Hello, my dear students. Today's lesson is going to be slightly different from the others, and you might have noticed that I'm speaking English. It's because of the great number of my students living in other countries whose native language is English, and they have asked me to translate at least a couple of lessons into English so that they can get what I'm talking about while I'm explaining um, a solution to another problem. Uh, I hope that my Russian students, Russian-speaking students, will not experience great problems because it's not a great challenge to understand, to comprehend English these days because English has become an international language around the world. Well, anyway, if some of you haven't been unable uh, to comprehend something, so you may ask me in your comments below the video. Okay, now. However, I want to say that the text of a problem will be in Russian, but the whole explanation will be in English. Okay? What is the way out of this seemingly baffling situation? It is that we are going to use mathematics, and in my opinion, mathematics is a truly international language among scientists, in particular among chemists and physicists, right? For that reason, whatever I'm writing on the board will be comprehensible to everybody who knows mathematics. Okay, now the text of a problem, I'm going to translate it into English right now. We've got a system in which a unimolecular consecutive reaction occurs, and the scheme of this reaction is represented here. And it's also known that the initial concentration of the reagent A is equal to 100 of moles per cubic meter, and the rate constant of the forward reaction is K1 is 0.25 minutes raised to minus 1, while that for the second stage of the reaction is equal to 0.95 minutes raised to minus 1. They ask us to calculate the concentration of the product C at the time when the concentration of the intermediate in the system is the largest. Okay, this is it's what the problem is itself about. Now, in one of the previous lessons, I already derived all the formulas we need when we're dealing to one of the three main cases of complex reactions. In this particular case, we are dealing with a consecutive reaction because we've got the intermediate B, the initial reagent A, and the final product C. Now, also we've got a clue in the problem itself. They say that we are supposed to calculate the concentration of product C at the time when the concentration of the intermediate is the largest, and we know the formula. T max, yeah, is equal to the natural logarithm or logarithm with to the base e of the ratio K2 over K1 divided by the difference between the two concentrates, right? And we know all the values which are incorporated into this formula, and if we get armed with a calculator, so we can get the value of T max. This is the time when the concentration of the intermediate is the largest. So let's do that. 0.95 over 0.25, right, and 0.95 minus 0.25. So, and my calculator says that it is as much as 1.91 minutes. Okay, so that means that at this particular time the concentration of the intermediate, this B, is the largest, and we don't need to calculate the concentration of B itself. Absolutely no need to do that. All we need to do is to know the formula enabling us to calculate the concentration of the product at any time. And again, I want to say that I'm referring to one of the previous lessons where I derived this formula. Here it is. So the concentration of C at any moment t is equal to the initial concentration of the reagent multiplied by minus exponent raised to minus K1 times T, okay, minus, and we've got the ratio of K1 over K2 minus K1 multiplied to exponent to minus K1 times T minus exponent raised to minus K2 times T. Okay, we've got K1 and K2, here they are, okay, and we have just calculated T, the time when the concentration of V is largest. So let's plug in all these values. We know this concentration too, here it is, it's 100, okay, 0.25, and instead of T we put 1.91, okay, then minus 0.25 over 0.95 minus 0.25, okay, 1.91 minus exponent raised to minus 0.95 times 1.20, I'm sorry, 91. Yeah, okay. So if you get armed with a calculator, you will get the right answer immediately. So my calculator says that it is 21.63 moles per cubic meter. This is the right answer to this question, to this problem. Some of you may ask me, George, why are you using so strange, so odd measurement units, moles per cubic meters? Because we have got accustomed to dealing with moles per liter. You are dead right indeed. Most chemists and physicists, no, chemists actually, are accustomed to using moles per liter. However, it's not a great challenge for us to do that, knowing that a cubic meter contains 1,000 of liters. That means that this is the clue. If you want to transform these measurement units into something which is more appropriate for you, or which seems more appropriate for you, so it's not a great problem. All you need to do is to divide this value by 1,000 and we will get the right answer in terms of moles per liter. That's it. So this is the first problem, okay, and now we're going to proceed to the next one. Thank you.